Okay, let's work on the example 8.6.3. We are asked to find the inverse matrix of this A. So what I'm going to do, I'm going to copy down each element of these three rows of the number in here: 220, negative 211, 301, and then I'm going to copy down top two rows to the bottom. If I do 220, negative 211, now I'm gonna just draw a diagonal line upper left to the lower right, covering three numbers. This is the first number, we can cover 3. This is the second line, we can cover 3. This is the third line, we can cover 3 numbers, and we're gonna multiply them. So 2 times 1 times 1, that is 2. Negative 2 times 0 times 0, 0. 3 times 2 times 1, 6. Now, I'm going to do the same thing. For this time, I'm going to go opposite diagonal way. Upper right to the lower left and covering 3. So this is 1, this is 2, this is 3 lines. For this time, I'm going to put negative of those multiples. Okay. So I didn't write it on the first one, but these are the positive ones. And the left side, that's the negative one. 0 times 1 times 3, that is a 0. 1 times 0 times 2, that is 0. 1 times 2 times negative 2, that is a negative 4. Now, we just need to add all of those numbers to find the delta. So delta is a 0, 0 plus 4 from the left side, and then plus 2 plus 6, that is 12. That is the determinant of 3 by 3 matrix. Next, I want to find a transpose matrix. So I want you to circle this and make put some stars around this. So we need to do what? We need to find a transpose matrix of any given matrix. That's really important. What is the transpose matrix? This row to column. So we have a 2, 2, 0. We have a negative 2, 1, 1, and 3, 0, 1. Similar way what we did for the calculating of the delta, I'm going to copy down top two rows at the bottom: 2, negative 2, 3, 2, 1, 0. And also I'm going to copy down first two column to the right. So we have 2, negative 2, 2, 1, 0, 1, 2, negative 2, 2, 1. So this is our transpose matrix. And then we copy down top two rows at the bottom, and then first two column to the right. That's what we did. Once you create this, we're going to cross out the first row and then first column. Now we are ready to find the inverse of matrix, which is 1 over delta. And then each element inside of this matrix is gonna coming from the rest of these numbers. So what we want to do, I want to use these four, and then using AD minus BC. So AD 1 times 1 minus BC 1 times 0. That's what we did using these the four numbers. The middle one, I'm going to use these four. AD 0 times 0 minus BC 2 times 1. And then the first row, the third column, I'm going to use these four. AD 2 times 1 minus BC 0 times 1. Similar way, the second row, I'm going to use these guys. So AD 1 times 3 minus BC 1 times negative 2. The next one, I'm going to use this guy. AD 1 times 2 minus BC 0 times 3. And then I'm going to use this guy. AD 0 minus 2 minus BC 1 times 2. And similar way, the third row, you can do it. So I'm going to just write them out. Negative 2 times 0 minus 3 times 1, 3 times 2 minus 2 times 0, 2 times 1 minus 2 times negative 2. So we have delta is what? 12. So 1 over 12, we have 1, negative 2, 2, 3 plus 5, 2, negative 2, and then negative 3, 6, 2 plus or 6. So once you get to this, and you just keep it like that, and then your answer should be distributing these guys inside, but you don't have to. So this row operation technique, if you are given equations of a11x plus a12y plus a13z equals some number k1, we're going to take the coefficients of this x, y, and z, and you do the row operation. Basically, going from here to here is applying Gauss-Jordan elimination method. After you apply Gauss-Jordan elimination method, you end up getting this guy, and this portion, right side of the number, that's going to be your A inverse. Let's do this. So we need to set it up as a 1, 0, negative 1, 0, negative 2, 1, 2, negative 1, and 3. Bar, we need to put identity matrix, 3 by 3. So in the diagonal way, it's going to be 1 and then all others 0. So for here, the left side, the 3 by 3 matrix, what we want to do, we want to make this left side of the 3 by 3 matrix as an identity matrix. Okay, so all of this guy, our goal is to 1, 0, 0, 0, 1, 0, 0, 0, 1. That means we are applying Gauss-Jordan elimination method in here. So first, 1, we want to make this as a 1. If it's not 1, you're going to just switch rows to make a 1 or divide the whole row by whatever that number so that we can have 1. We already have 1. That's good. And underneath, we need to make this 0. We already have a 0. That's good. And the third row, we need to make it 0. So what I'm going to do, R1 times negative 2, and then plus R3, put it back to R3. Again, in this Gauss-Jordan elimination method, these two row numbers should be matched up. That's the important. You cannot just mix it up with any other numbers. You need to add the R3, then you need to put that into R3. You need to add that to R2, you need to put that in R2. R1 times negative 2. So negative 2, 0, positive 2, negative 2, 0, 0. And then R3, we have a 2, negative 1, 3, 0, 0, 1. And we're going to put it back to the matrix. 1, 0, 0, 0, negative 2, 1, 0, 1, 0. And then this guy is going to be here, which is 0, negative 1, 5, negative 2, 0, 1. And then the next, we want to make this guy to be 1, right? I need to divide everything by negative 2 or multiply negative 1 over 2. So 1, negative 1 over 2, 0, negative 1 over 2, and 0. Now we have to use R2 to make upper number and lower number to be 0. Well, we already have an upper number as a 0. Yay. Just copy this down. And then third number, we want to make this to 0. We need to use R2. So R2 times 1 plus R3, put it back to R3. So R2 times the positive 1. So we're going to just copy down R2, 0, negative 1 over 2, 0, and R3, 0, negative 1, 5, negative 2, 0, 1. And when we add, we have a 0, 0, and this is positive 10 over 2. So we have a positive 9 over 2, and then negative 2, negative 1 over 2, and 1. So we are done for first two column, right? So now we need to work on the third column. To work on the third column, we need to pick third row, third column, this guy. We need to make this to 1. We're going to multiply 2 over 9. Then we have a 0, 0, 1. Negative 2 times 2 over 9. So negative 4 over 9. And then negative 2 and 2 cancel, negative 1 over 9. And we need to multiply 2 over 9. We need to work on this guy, right? To make this to 0, we need to use all 3 times this. We have a positive 1, so we don't have to do anything. I just put it 1 there. And then add to R1, put it back to R1. So R3, we have a 0, 0, 1, negative 4 over 9, negative 1 over 9, positive 2 over 9, and we have R1, 1, 0, negative 1, 1, 0, 0. When we add, we have a 1, 0, 0, and then this is 9 over 9. So we have positive 5 over 9 and negative 1 over 9 and positive 2 over 9. And the second row, the third column, we have a negative 1 over 2. So I'm going to use all 3 times positive 1 over 2, add to R2, put it back to R2. So all 3 times 1 over 2, 0, 0, 1 over 2, minus 2 and 2, 2 over 9, minus 1 over 18, plus 1 over 9, and R2, we have a 0, 1, negative 1 over 2, 0, negative 1 over 2, and 0. We have 0, 1, 0, and negative 2 over 9. And for this guy, negative 1 over 18 minus 9 over 18. So it is negative 10 over 18, which is negative 5 over 9 and positive 1 over 9. So the A inverse is this guy. As you can see, if you use row operation to find the inverse matrix, you have a 90% chance that you have to deal with these fractions. So let's do this. So the method that we learned, we can find the delta. How? Copy down 1, 1, 0, negative 1, 0, negative 2, 1, 2, negative 1, 3. Top 2 rows at the bottom, 1, 0, negative 1, 0, negative 2, 1. And then diagonally, this guy, 2, those are the 3, and they are plus negative 6, plus 0, plus 0. And the opposite way, we have a negative, negative, and negative 4, right? And then this 1, 1, 1, negative 1, this one is a 0. So our delta equals to negative 1 plus 1 minus 6. So that is negative 9 as a delta. And then A transpose 1, 0, negative 1, 0, negative 2, 1, 2, negative 1, and 3. Copy down top 2 rows. 1, 0, 2, 0, negative 2, negative 1. And then first 2 columns, 1, 0, 0, negative 2, negative 1, 1, 1, 0, 0, negative 2, and then scratch out. So now we want to do inverse matrix, which is 1 over delta. And then when you do AD minus BC, negative 6 minus minus 1, and this AD, negative 1 times negative 1, which is 1 minus BC, and then AD 0 minus BC, negative 1 times negative 2, that's a positive 2, and then AD 2 minus 0, 3 minus minus 2, 0 minus 1, 0 minus 4, AD 0 minus minus 1, AD negative 2 minus 0, negative 5, 1, negative 2, 2, 5, negative 1, that's positive 4, that's a positive 1, that's a negative 2. Okay, when you compare with this, after you factor out negative 1 over 9 as a delta, you should have all of this number. Now, I give you 3 equations and 3 unknowns, and I'm going to ask you to find the solution, meaning find the x and y and z find the solution using inverse matrix. It said using inverse matrix to find the solution. Then you have to go use that inverse matrix. So if we put this into the matrix form, we're going to take the coefficient that is 1, negative 1, 1, 2, 1, 2, 3, 2, negative 1, and then times x, y, and z, and that's equal to the right side of the equal sign. You have that. And in order to find the value of x, y, and z, you need to divide both sides by with this guy. So this guy is in front of the x, y, and z. That's why you need to put this in front of 1, 2, and negative 3. If you switch these two, then you won't be able to calculate the multiplication. Why? Because we said for the matrix multiplication, the dimension has to be match up. This is 3 by 3, and this is 3 by 1. The inner number, they should be the same, and the result is going to be the outer number. If you switch them around, you have a 3 by 1 matrix times 3 by 3, and inner numbers, they are not the same. You cannot multiply these two matrices. This is the problem 8.6.50 and also in the YouTube. So I'm going to just work on this, just maybe one or two coefficients are different so that we can actually practice this. And I want you to practice this problem again. And then if you get wrong, please check for the YouTube answer. So in order to find the solution, we have to have x, y, and z equals the coefficient 1, negative 1, 1, 2, 1, 1, and 3, 2, and 2. We need to find the inverse matrix first, and then we need to multiply that by this number. So let's find the inverse matrix first. So the A is given as 1, negative 1, 1, 2, 1, 1, 3, 2, 2. To find the delta, I'm going to copy down top two rows here. 1, negative 1, 1, 2, 1, 1. And for the diagonal, and these are the plus, and then this diagonal, and these are the negative. So the positive one, 2 times 1 times 1, 2, 2 times 2 times 1, 4, and negative 3, 3, 2, 4, negative 4. So our delta is negative 3, negative 2, positive 4, plus 2, plus 4, negative 3. That is 8 minus 6. So 2. So our delta is 2. And then we need to find 8 transpose, row 2 column, 1, negative 1, 1, 2, 1, 1, 3, 2, 2. Top two rows, 1, 2, 3, negative 1, 1, 2. First two column, 1, 2, negative 1, 1, 1, 1, 1, 2, negative 1, 1. Scratch out first row, first column, and then our inverse matrix is 1 over delta AD minus BC, 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 AD minus BC. So our inverse 1 over 2 times, we have a 0, 4, negative 2, negative 1, negative 1, positive 1, positive 1, negative 5, positive 3. And then we need to multiply that by negative 1, 3, and 8. I'm going to write x, y, and z equals A inverse 1 over 2 times 0, 4, negative 2, negative 1, negative 1, 1, 1, negative 5, 3 times, we send negative 1, 3/8. If you distribute this 1 over 2 inside of this inverse, you have to deal with all these fractions. But I'm going to just keep it in something like that, so that I'm going to multiply that 1 over 2 at the very end, okay? And this is 3 by 3 matrix, and we're going to times 3 by 1. Inner numbers are the same. Then result is the outer number, which is 3 by 1, and that is 1, 2, 3. And that is row by column 0 times -1 plus 4 times 3 plus -2 times 8. That's the first row. And then second row, this times this. That is -1 times -1 plus -1 times 3 plus 1 times 8. This row by column. So 1 times -1, -5 times 3 plus 3 times 8. So 0, 12, minus 16, and 1 minus 3 plus 8. Then -1 minus 15 plus 24. X, Y, and Z equals 1 over 2 times, that's the -4, negative 9, 9, so 6, -16, so it's going to be 8. So from here, X equals to -2, Y equals to 3, and Z equals to 4. So that's your final answer. Cramer's rule. When you have a n number of linear equations with the n variables, and you can use Cramer's rule to find the x1, x2, x3, x4, ax plus by plus cz equals to k1, a2x plus b2y plus c2z equals to k2, a3x plus b3y plus c3z equals to k3. So for this class, you'll be given 3 equations and 3 unknowns again. And I can ask you to find the solution using Cramer's rule. So what you need to do delta, delta 1, delta 2, and delta 3. That's what you need to find. You know how to find the delta, right? Take the coefficient of this x, y, and z and copy down top 2 rows, multiply diagonal way. And I'll show you how to find the delta 1, how to find the delta 2, how to find the delta 3. Once you get to that, then x equals delta 1 over delta. Second variable y equals delta 2 over delta. Third variable z should be delta 3 over delta. So this is the Cramer's rule. So again, this is the extension of the finding inverse matrix using the technique that we learned. So let's do this. So copy down all the coefficients. So 1, -1, 6, -1, 2, 4, 2, 3, -1, and copy down top 2 rows. 1, -1, 6, -1, 2, 4. This is positive, 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 and we have negative, negative, negative. So the positive one, -2, -18, -8, 24, 12, and this is -1. So our delta equals -24, -12 plus 1 minus 2 minus 18 minus 8, -63. So that's our delta. So it's the same delta when you calculate the inverse matrix. Now we want to do delta 1, right? So now for the delta 1, and if it's delta 1, the first column, we're going to use this number. So that is -2, 9, 1 over 2. And the second column and third column is the same. -1, 6, 2, 4, 3, -1. Copy down top two rows. So -2, -1, 6, 9, 2, 4, and then diagonal. That should be 173. For our delta 2, this time, since it's a 2, the second column, we have a -2, 9, +1/2. In the first column, we still have a 1, -1 and 2. Third, 6, 4, -1. And you copy down top two rows, 1, -2, 6, -1, 9, and 4. And you do it, delta 2, you should get 136. And delta 3, you do it, and you should have 61/2. And for the x equals delta 1 over delta, which is 173 over -63. And then y equals delta 2 over delta, that is -136 over -63. And finally, z equals delta 3 over delta, and -61/2. And you said delta is what? -63. The last section for chapter 8 is eigenvalues problem. So it is often important to find there is a non-zero sum matrix that when you multiply the matrix A times any very specific number, that result is this lambda of this k. So we can separate. After you multiply this number, we end up getting some constant times that number. So in order to find eigenvalues and eigenvectors, you need to go through two things. So we need to use this to find the lambda. This is our what we call characteristic equation. So using this to find the lambda, and that is the eigenvalues. And using this eigenvalue into this, we saw this when you try to solve for using Gauss-Jordan elimination method. We use the bar and put the right side of the equal sign number on the right side of this bar, but we're going to use 0. So you need to know these two equations. So to get the eigenvalue, you need to use that. To get the eigenvector, you need to use that. So for the first example, you are given one eigenvector. If this is the real eigenvector, then when you multiply this A times this K, the result is going to be some number times this eigenvector K. So we use this eigenvalue and eigenvector for many different applications in the engineering field. So one example is in the control. We want to design some subsystem. What I want to do, I'm going to go through any signal, this subsystem, and the result of this subsystem is going to be amplified the input. So if you have a small signal, the amplitude is very small or the noise is very small, I want to multiply that with some number so that I can get the magnified that input. So if that is the case, we can find this eigenvector and multiply to the system. The result is so some magnitude. So in this case, -2 could be +10 times whatever the k values. So we can control the output based on these eigenvalues and eigenvectors. So we can multiply input signal to find the magnitude of the 10, or we can just reduce the noise by half and so on. Let's do this. So here is the matrix A is given as a 3, 4, -1, and 7. And you are asked to find the eigenvalues and eigenvector based on this matrix A. So this is the system. I want to find the eigenvalues, and using eigenvalues, I want you to find the eigenvectors. What we need to do, we need to do determinant of this guy. So that means we have a 8, 3, 4, -1, and 7 minus lambda times we have I, right? That's the identity matrix. So lambda times, since we have A as a 2 by 2, our identity matrix should be 2 by 2, 1, 0, 0, 1, and that equals determinant of 3 minus lambda, because if you multiply this lambda to this identity matrix, we're going to have a diagonally lambda, right? Because 1 times lambda is a lambda. So in the diagonal, we have a 3 minus lambda, 7 minus lambda, and we're going to have 4 and -1 as they are. And this is the determinant. So AD 3 minus lambda times 7 minus lambda minus BC minus 4. And that equals 21 minus 10 lambda plus lambda square plus 4. And that is lambda squared minus 10 lambda plus 25. If you factor out, that is lambda minus 5 squared. So from here, we have lambda 1 equals to 5 and lambda 2 equals 5. Very good. So these are the two eigenvalues. Once you have two eigenvalues, you need to give me two eigenvectors. Even though they are the same, eigenvectors is going to be two different eigenvectors. How? Well, you will see. So now, to find the eigenvectors, we have to use this. So we're going to have A, again, we have 3, 4, -1, 7, minus lambda I. So this time, we're going to write lambda 0, 0 times bar of all this. So for using first lambda 1, which is 5, you're going to use this as a 5, this as a 5. Then we have 3 minus 5, -2. And then 4 minus 0, 4. And -1 minus 0, -1. 7 minus 5, +2. And then bar 0, 0. So now you need to use Gauss-Jordan elimination method in here again. The Gauss-Jordan elimination method, what do we need to do? We need to make first row, first column to be what? 1. Then we have 1, -2, 0. And we need to make this, the one below 1 to be 0, right? So I'm going to use R1 times 1 plus R2, put it back to R2. R1, we have a 1, -2, 0. R2, -1, 2, 0. When we add, we have a 0, 0, 0. So this is this where we have many solutions, right? So beginning of this class, I talked about many solution versus no solution, because we have a left side of the 0 and the right hand side of the 0. So 0 equals to 0. So we have unlimited number for x and y in this case. So to find the x and y, what I'm going to do, I'm going to call it this row as a lowercase k1, lowercase k2, and then simply multiply these two. So we have 1 times k1, k1, minus 2 times k2, that equals to 0. So from this relationship, we have k1 equals to 2k2. So as long as your vector satisfy with this condition, you're just fine. So you need to show me this expression first. So based on this, capital K1, that's your first, the eigenvector. And in this eigenvector, you can just use this relationship. So you can just, let's say, let K2 equals to 1. Then K2 equals to 1. Then K1 is what? 2 times 1, which is 2. Since we have the same value of two eigenvalues, so you just need to give me one more K. You can just pick any. Let K2 equals 1 over 2. Then K1 equals to 1. So again, there are unlimited number of this case, but you need to show me just two because we have a two same eigenvalues. If they are two different eigenvalues, then you need to use two different relationships to give me two different eigenvectors. So this is your final answer. So I want to see how you calculate this eigenvalues first using what? Using this relationship, and then each eigenvalue you end up getting something like that. And once you know finish Gauss-Jordan elimination method for 2 by 2, always the second row is going to be 0 rows. Always. I said always. If we have a 3 by 3 matrix, you end up getting one row of 0 or two rows of 0. So you have to have minimum one row of 0. That's going to be the case always for when you're calculating the eigenvectors. You have row of 0, so that you need to find relationships between k1 and k2. And if you have a three different variable, you have a k1, k2, and k3. Good. I forgot to mention that you can use any values of k2 to get the capital K1 and k2 except 0. 0 is not allowed. You cannot let k values as a 0. Thank you. You can use negative value, you can use negative fraction, you can use 1. Okay.